Today is June 8th, 2021, and I'm going to do some finalizing, you might say, of these SET amplifiers I've been building over the last year or so. Here's the 300B. It does a good 7 watts per channel. I'm very charmed with it. And here's one I've been working on for some time, and I have to have help to move around. This one is using the, let me turn the lights on here. This one is using the Svetlana 572-10. It means it has a gain of 10, the big triodes right here. They run at 1,000 volts, actually about 1,090, almost 1,100 volts. The driver is a 6SN7. It has to drive a 5881 or a 6L6 to get the voltage up high enough to drive the grids. These types of tubes run what's known now as A2, meaning, I think that's a bogus terminology, but it means they draw grid current. You have to drive the grid positive. That's why you have to have, you could easily use a cathode follower, or you got to have enough power, actual power, not just voltage, to drive the grids of tubes like this. You'll see this thing's pretty magnificent. I remember when I first showed this one in its infancy, a good gentleman said, yeah, 20 watts per channel for an SET is pretty challenging. Well, it certainly is. But this is not the one right now. We want to examine them closely, one at a time. This is one we want to do first. We're going to look at the Harmonic Profile, which I think is probably the most revealing characteristic about them. Both of these amplifiers have a choke load for the plate. I did not choose to use a standard high-gapped SE type transformer, although I do have them. I ordered them special order right here from a good gentleman over in Poland. These things perform wonderfully. I have actually put them in. These are, I guess, 10 watt gapped SE transformers. They're very heavy. They're very good. These are the 10 watt non-gapped ones. I wanted to see the difference because the way that I've got these set, see, I have a pair of them, a pair of the gapped ones and a pair of the non-gapped ones. We're not going to have them in here, although I have tested them, and for all practical purposes they perform exactly the same. You're just going to take my word on that because I'm not going to put them back in there. The plate load is this choke. This is a 15 Henry. See, there's a pair of them. They're very nice. And then the output that's developed across this choke has got a blocking capacitor into this James transformer, which is an impedance matching device, so I can get 8 ohms out the other side. This is a power transformer. Very powerful little power transformer. Come out of some surplus equipment from Sandia Labs. I use it as a voltage doubler. Single 6SN7 driving the right channel. Another single 6SN7 driving the left channel. Actually fairly simple. Here's the schematic to it. It's easy to drive. I've got 200 millivolts drive. We're also going to look at the LT Spice model of it. 100K input, 220 ohm cathode resistor, 75K plate load resistor. Over here, 22K, 51K, etc. I found out that a very high load resistance, so that we're not loading this circuit at all, I used an 8.2 meg. Most of this was designed empirically. We're only developing a voltage across this grid because it's running at minus 60 volts bias. And if you look at the plate characteristic curves of a 300B, you'll see that at minus 60 volts bias, you can drive at plus 60 volts, which would be right at 0. You don't want to drive it past 0, you start driving grid current. And you can drive at minus 60 more, which would be minus 120 volts, and it's still very linear. 300B is a beautiful tube. Truly is. Here's the plate load. So the voltage and the power out of this tube is developed across this choke. That's these guys right here. And then underneath there's a couple of capacitors, electrolytic capacitors in series, which makes a non-polarized blocking capacitor. One of the things I found out about this the hard way is when this thing is running, these capacitors charge up, and when you turn it off, they don't discharge. There's no path for them to discharge, and they can hold quite a wallop. They'll surprise you. And here's the 20 Henry to 40 millihenry. That's the ratio of I don't remember whatever that ratio is, impedance. You can turn that back into whatever you want, into an 8 ohm load, and a feedback resistor. That's not correct right there. I got it as 1E12. I got that as a trillion ohms. I don't remember what I've got it set at. I'll have to correct that in the model when we run it inside. I did not go to the trouble of building the power supply and all of its detail, because as LT Spice comes up, it wants to see the voltage and it's simulating the voltage coming up in the power supply, and it just causes a whole lot of complications that we don't need. We're not interested in how this power supply comes up in a couple of milliseconds. So I just put it in as a DC source, 416 volts. A 1 Henry power supply choke, 50 microfarads off of each side, etc. That's pretty much it as far as the schematic goes. Left input, right input, left gain, right gain. Pretty simple stuff. Pretty standard stuff, I guess I would say. Let's look at the back. We're going to look under it because I got some unique details underneath that I think you'll like. I have shown this one before, so this is a little bit of a review. 8 ohm output here, 8 ohm over here. You don't have to run it at 8 ohms. You can run it at 16. Seems to perform just as well, if not a little bit better there. Power on and off. I'm not going to turn it on. Let me unplug it here. And then I've got a negative feedback switch in here with no negative feedback at all. If you want to go that pure, or 7 dB. Just a little bit of negative feedback does help. It does help. And I put some notes up here. If you can read that, it says 45-second delay for ready. I give it 45 seconds for it to warm up before I put the high voltage on these tubes. Now these are some pretty fancy tubes. They're quite expensive. These are the Gentle X 300Bs. I've had 4 of the, I believe they're Harmonics to use in this, and of the 4, 2 of them have already gone bad. One of them sparkles inside as it powers up, and the other one, half the filament is out. So that's sad to say, but I'm not terribly impressed with them as I thought I would be in the beginning. Okay, let's look underneath it, because I think underneath you'll find some interesting stuff. Okay, all I've done here is remove the 4 screws in the bottom, so I can remove the bottom. I put a schematic on it, so in case I need it in the future or somebody else gets a hold of it, they'll have some idea of how it's built. It may be changed somewhat. There could be a component value that's different than this schematic shows. It only shows 1 channel too. Doesn't show the power supply detail. But anyway, it's something. Okay, well here are those blocking capacitors. See, they're 2 in series. You hook the plus to the plus, so you have 2 minus sides. Minus is the minus side, one capacitor, and the minus side to the other capacitor, the negative side. That's what you put in series with it. You have to put it on something to insulate it, because these little capacitors oftentimes have no insulation on the bottom, and even if they do, it's not enough. It can arc to the chassis. So there's 1 channel. Here's the other channel right here. So here are the matching transformers. Here's the main power supply and its capacitors. Nothing too weird about it. Hum balance right there for the 6SN7s. Here's the power supply choke. As for the filaments of the 300Bs, I always run them on AC. I do not have a problem with hum. I do not go to the trouble to put DC in them. It is not necessary. However, it is necessary to put a balancing pot on it. This is a 50 ohm 5 watt pot, and the center of it actually goes off. See, one side of the pot is hooked to one side of the filament, the other side of the pot is hooked to the other side of the filament, and the wiper on it actually goes off to the bias network right here. It's cathode biased. Here's one resistor and its capacitor, and the other resistor and its capacitor, and you very carefully set this thing for the least amount of hum, and you don't have to convert it to DC. You need to do the same thing down here. This one is very insensitive, but it does make a little difference. These are very sensitive. It is necessary to put a hum balance pot in on the filaments if you run them on AC, and it works great. I did not have a 5 volt transformer, so I used a 6 volt. This one's got dual primary, dual secondary, etc., and then I just put a voltage dropping resistor on the primary to get the voltage down to 5 volts. So this is a 6 volt, I think 10 amp, pretty hefty little guy. So that's where I get my 5 volts without having to go to the expense of, you know, throwing away a lot of money. Okay, to delay the DC from coming up, I've got a delay relay here, a little 115 volt delay relay. You put 115 volts on the filament, and after whatever its timeout is, this one happens to be a 45. The larger ones, this one would be known as a 115 NO45. That means it's got 115 volt coil. NO means it's normally open, and the 45 says it takes 45 seconds to close. And then when this, when the time expires in this and the contacts in this little thermal relay do close, it pulls in that relay, and then this relay has got a set of contacts that latches it on. So it's a little latching relay circuit controlled by this thermal relay. I like the filaments to be up before I throw the high voltage to it. It's not terribly high, it's just a little over 400 volts. I don't think there's anything else. I use these, I point this out each time, I use these little IEC type power connectors. That way when I'm moving the amplifier around, I'm not dragging this power cord. See, when I take the speaker wires off, the thing is completely free. And you're not having to worry about tripping over the power cords. Naturally a fuse. You gotta have a fuse, or things will go things will eventually go wrong and you'll regret it. See, there's those 8.2 mega ohm resistors I tell you off the grid. Now in a real Class A amplifier, you never draw any grid current, so you never have to provide any power to the grid. You just have to provide voltage, and you want to provide a perfect voltage. And I found out that a very high load resistor right here for the grid circuit is what works best. You do have to have a resistor there. You can't leave it open, or the grid will end up with a charge on it and the tube will cut off. It won't hurt it, but it'll just quit working. So here's the inductors, the plate load inductor here. The other one's over here, underneath there. It's all drained, so I don't have to worry too much about it. Cathode resistors, there's one channel. There's the other channel. Here's the input. So there you go. That's that. Okay, let's do a little bit of testing. Put the bottom back on and flip it back over, and we'll see how this thing performs. Okay, we'll start out with some static test first, and then we'll be looking at the Harmonic Profile. I've got two programs for Harmonic Profile. This one is a program called True RT8, quite nice. And then I also have the Spectra Plus down here, which is that one. So they're both running at the same time. I've shown all this before, but for new viewers, the output here of the amplifier, as you can see, is connected here in the back, connected up here and right over there. All runs up to these precision resistors. They're 8 ohms, 350 watts, I believe. 300 watts. They have a very good temperature coefficient, meaning they do not change in resistance when they get hot. They're not terribly expensive. They're like 60 bucks a piece, and they're mounted on a heat sink. So this is the wires that feed them up there, and then this is the one that goes over to the equipment where we're doing all the measurements, and I can switch from left channel to right channel just like that. Okay, we're looking at the left channel now. Left is to the left and right is to the right. Trying to keep it simple. Okay, now first thing we're going to do, we're going to use this little Tektronix SV505, which has almost perfect harmonic profile, something like 8 parts per million. And what we're seeing at the moment is 1.3 watts across an 8 ohm load. This is what it looks like. I know it's a little bright in the camera, but and its frequency right there is a kilohertz, and its THD is right there, 0.2%. So it's very good, isn't it? And we're going to run this thing up. We're going to run up the power. Let's see, let's put that right there. Let's run up the power until we start seeing some clipping, some distortion here. This thing is auto scaling, by the way. Okay, see how the bottom flattened out? That's one thing unique. I won't say unique, but it's different about SE amplifiers that push-pull. And a good push-pull amplifier, that the top and the bottom clip symmetrically. But in an SE amplifier, one or the other, depending on the phase you're looking at, clips. So we'll take the clipping out to about right there. And there's pretty much its maximum power, as I see it, of 7 watts. And THD is actually up at 3.8%. And it looks really good. But, you know, this audio analyzer is called an AA501. It's telling us the truth. But to our ears, I think our ears will be quite happy with that. Actually, I think our ears would probably be even happy with that. Actually, not much more power. 7.3. We're up to 7% there. Okay, that's at a kilohertz. So that's the basics. That's where you would start. So I'd call it a 7 watt amplifier per channel. Okay, that's the left channel. Let's go over here. We flip this switch right here, and we go to the right channel. And run it back up to where, see, we get this thing bottom getting kind of flat. Take it right before that, and we got 7 watts again at the same distortion level. So we can flip back and forth and see it. This right here is measuring the AC voltage. Got pressed around, that's its voltage. You could square that, divide it by 8, and you will get that number right there. Okay, let's look at its harmonic profile. Holy kitty cats. Well, this is its fundamental frequency right here. This is its second harmonic, third. Because see, this is at 1 kilohertz. Hope you can see that. 2 kilohertz, 5, whatever, 2, 3, 4, 5, 6, 7. It's all there, isn't it? That is a lot of harmonic content. But that's what it is. Now over here is 60 hertz. This is our hum, but you see it's down. It says minus 55, so it's down. Well, let's see. Our power is up here, not quite to 10. Let's call it 10 to estimate, and we'll call this up to 55. So it's down 65 dB, thereabouts. And that little hum pot I was showing you in the bottom, that filament hum pot, that's what you would adjust. And you can see this go up and down, and you'll set it for a minimum. Or you can just put your ear up to your speakers and turn it. And that's the way we did it in the old days. We adjusted the hum pots until the hum went away as you hear it. Well, this is with the True RTA FFT program. Just for fun, let's go over and look at the Spectra Plus, and that's what it looks like. Got a little sharper display, but it's telling us the same thing. See, this one is not up to 0. This one is down a little bit below minus 10, and then this one is below, a little bit below minus 70. So it's the same numbers. Whichever one we like. This one's flickering a little bit more, so I think we'll go back to this one. They're telling us the same thing. Look at this harmonic profile here if you want to see that. See the second and the third is up, and then it kind of has a linear taper to it maybe. And let's see what this one looks like. I mean, same thing. Second one's down, the third one's up, and then it tapers off. Looks like the sixth harmonic is down. The sixth and the eighth are down kind of in an interesting there. Let's look at this one. I'm sure it'll tell us the same thing. Yeah. See, there's 6, 7, and 8. Okay. So we have two spectrum analyzer programs telling us the same thing. Okay, now last, I think what it deserves is it deserves a scan. I've already scanned it, but I'll scan it again real time and show you. This is what the scan looks like at 5 watts. I'm going to test everything at 5 watts. This is not a video of how much power we can get out of it. This is a video of 5 watts is a good listening level in a room if your speakers are reasonably efficient. 1% right here. I ran both channels. I think I'll run one channel twice. That's one of those 3 traces there. But it looks like it does 1% or below between 60 hertz and 10 kilohertz. Now that's not the 20 to 20 kilohertz perfection that we think that we all are supposed to have. But that's the way it plays out, ladies and gentlemen, and sounds fabulous. So it's not all about THD. Okay? But we want to run this real time so that you can see exactly how it performs. So let me get it set up here. Okay, keep the video from being longer than is really necessary. I'm running right now, if you'll notice, I'm running the output of the analyzer right back into itself. It's just a self-check, you might say. See this yellow line that it's drawing out here at the bottom? It's testing itself, so we can see that it's working correctly. It says that the THD is below 0.1%. I mean, it's down there basically at 0. Now the way that I run it is I have to tinker with it a little bit, set the generator level, which is the output of the that HP 80, what is that thing called, 8902. I set it to 0.27 volts. I run it at 10 points per decade, which gives us a much smoother display. But like I said, I'm just testing it now. I want you to see. This gives us confidence that it's working and it's working properly, and we're not getting any distortion or whatever from the outside world. Up to 10 kilohertz. It'll be there in just a second. And we're scanning it from 20 hertz to 30 kilohertz. Now it may not actually run all the way out to 30 kilohertz, but that's a little program glitch. It's out at 20 kilohertz now. That's all we care about. Looks like it stops at 25.18 for whatever reason. It's completely unimportant. Okay, so now that we know that it works, everything is peachy, what we're going to do is run it for real. I just connected the output of the 8903A into the amplifier, and now we're going to run the second trace. See, this is the first trace, second, third, fourth, so we can run 4 traces. So all we need to run is 2. But let's see what channel. We're testing the right channel first. So this is the right channel. Well, maybe we are. Yeah. Oh, I don't see anything. Why do I not see anything? I don't know the answer. Well, I got the output to the input, and let's see, maybe I turned him all the way down. No. Well, anyway, I got to stop it and fix this part. Okay, well, I'll just leave that little blurb in there. It's okay. I forgot to hook the the output of the amplifier back into the measurement system. I had the output of the generator hooked directly into the measurement system. That's how we did this right here. When I disconnected, I forgot to hook it back. So now let's look at it again. This time we'll run trace 3, which is completely fine. Yeah, I see it running now. Okay, you see that purple line coming down? Coming down right here. This is 20 hertz. It's way up here, it's well beyond 3% at 20 hertz. Down below, here's 1%. Down below, it's coming down. I figure anything down here below a couple of percent, probably doesn't bother us very much. But 1% is kind of my benchmark. So it's doing pretty good. And again, this is at 5 watts. All of the tests we're going to run tonight are going to be at 5 watts. The reason 5 watts is because, like I say, that would be, I think, a reasonable listening level. I've got to show you here. I'll move the camera as the next one is running because I want you to see the display on the spectrum analyzer, how it's dancing across there. Okay, so we'll remember that the purple one here is the right channel, and it looks like it went over 1% right there at about 10, 9, 8, about 7 or 8 kilohertz. It's going back up. So there you go. Now it's finished. That's what I got a while ago when I run it. I've run it, you know, more than once before testing it, and that's what you get. Okay, let's go to the left channel and run it one more time. This will be the left channel. Again at 5 watts. While this thing's running, I want to show you. Here's our power right there. Oops. See the power? 5.18. Okay, and this is what it looks like dancing across the screen as we go to different frequencies. We're running each of these frequencies as it's scanning kind of slow at 10 points per decade, and like I say, that gives us a nice smooth display, and it'll run all the way out to 20 kilohertz. I would let you look at the other program running too, but I don't have enough hands. Okay, let's go back to what this piece of the video is all about. Right there, and here it is, the green one. See, it's actually running a little bit better. The left channel is performing somewhat better than the right. Could I move the tubes around? Yeah, but I'm not going to do that. I've done all this. I will say one thing about SE amplifiers. It's very different from push-pull, and that is the gain of each component. Everything is critical in these SE amplifiers. It's just kind of crazy to build these things if you really don't know how I feel about it. They're fun, and they've got a sound that's very neat. But that's it, ladies and gentlemen. That is quite a wonderful sounding 300B SET amplifier stereo. And we'll go back to here and let me zoom back out, and that's what it looks like. So for what it's worth, I don't think I'll build anymore, but let me get set up here and we will examine this beast right here. This one is a beast. By the way, before I completely go away, let me show you something about this one that you're going to find very different about the other one. This one is not too hot. It actually runs pretty decent. This one, let's see, can you see that? It says that tube is about 230 degrees, 240, 50 degrees, whatever. Same thing over there. Okay, remember that, about 230, 40 degrees. And we'll compare that to the next amplifier. Okay, I'm going to start out with this one by showing you underneath it first, so that when I set it down I don't have to set it back on its top or bottom or side again, and keep my light. My light will, there we go. Okay, well here's the schematic for it. I use a 1 megohm on the input, 6SN7, pretty much the same circuit as on the 6SN7 portion of it, pretty much the same circuits in the 300V SET. I have a gain control right here going into the 5881. The 5881 comes out and drives this 572-10, and I use a non-polarized capacitor here. I bought some instead of using two electrolytics, and then again, and then it's the same circuit. This is the plate load right here. This is the blocking capacitor, and this is the impedance matching transformer, and it has feedback that I can take out or in. I think I put 13 dB of feedback in this one to settle it down, so to speak. Okay, we'll look at it from the top. But again, you're going to see the same thing that you saw a while ago. Here's the pots, the filament pots to adjust a hum for the left channel and the right channel. And then for the 6SN7. So that part's the same. It's a duplicate. It's got a big power supply. It's got these three 450 volt capacitors in series, because this one runs at just a few volts shy of 1100 volts on the plate. The specs are 1000 volts. I think it's running at 1090. This right here is the secondary. This comes off of the center tap. See, what I've got here is a bridge. I've got an 800 volt 400 milliamp transformer and a bridge, and then off the center tap I go through another diode into a choke and its set of filter capacitors. This one is not used right here. I had that one on the input, but that raised the voltage too high, so this is the low voltage supply that provides the low voltage for this area up here is a choke input filter. These chokes right here, this one and this one, is what is the plate load for the 5881s up here. So these 5881s operate into this. I wanted to use inductors in all of this. Here's a coupling capacitors. They do not have to be 10 microfarads. 0.1s work just as well. That's true and not quite true. These 10 microfarad ones actually make the low frequencies perform slightly better. Now here it was very different. Now we're drawing grid current on this one when we start driving a grid positive, so you can't put that 8.2 megohm in there. I tried that. It doesn't work at all. It just doesn't work very well. That's a 47K. I tried lots of different values. Let's see, I have a 47K there. There's one over here for this channel. You know, this is left and right channel, and this pot right here, these pots right here, is that pot right there going into the 5881. There's an on-off switch. This is the switch that switches in or out the negative feedback. Power supply choke. I use cathode bias on it. Here's the cathode bias for one channel. Here's for the other. So remember, it's stereo, so there's a duplicate of everything in here except for the power supplies and stuff like that. Here are the blocking capacitors. These are 3.3 microfarad at 2000 volt. This is where the choke comes into the bottom and actually connects over to the plate of the output tube. So that's it. That's at the bottom. I don't have a bottom plate for it in the schematic attached to it yet. That's for a later date when I get some help in manipulating this thing. Here's my input circuits over here. 1 megohm pots. And I use shielded cable from there over to the grids of the tubes. So let's flip it over. Okay, well, let's see how this one turns out. It's impressive, I'll tell you. Let's turn the lights out and see what these tubes look like. After they've been on long enough, yeah, you can see that they're just on the verge of running orange. This I can see it pretty clearly here. This is the first time I've made a video of it, so I can see it pretty clearly here in the video. This camera seems to be really sensitive to infrared, but you can see that they're actually, you can see how hot those plates are. This thing's like sitting in front of a heater. I'll show you the temperature once it's warmed up for a while. Which makes me think of these people that build all these things with these 100 THs and 304 TLs and 833s. I have an 833 amplifier in the basement that I run on 20 meters. And it delivers an easy 1,000 watts to the antenna, and it is hot. Of course, I blow fans over it and everything. It's a big tube. But this is a very, very hot amplifier. Like I said, it's like sitting in front of a heater after it gets really warmed up. Okay, so that's that. I'm going to try to go by exactly the same format as I did a while ago. This is not important right now, but there it is running on the analyzer. And here it is over here. We're going to start out by testing it at 1 kilowatt. That's its power, 3.4 watts. There's its frequency, and there's its THD. It's actually pretty good, isn't it? Okay, let's see if I can do this without dropping the camera, wiggling it too much. Let's run it up until it starts, flat topping. There we go. See how, whoops, I got loose connections here. It's flattening off there. Well, there's our, I mean, we can actually get 20 watts out of it. There's 20 watts. Got a little kink at the top. If we take the kink out, about right there, we got right at 18 watts. That is the left channel. There's right channel. Does the same thing. That was actually quite a chore to get that exactly right. What it took to get that correct, not correct, but to get them equal, was swapping lots of different 6SN7s in, so I ended up with the same gain on both. And also putting in the negative feedback. It does have negative feedback in it now at about 13 dB. So there it is. There it is running at, let's run it right at 18 watts just cause. There it is, a little over almost 20 watts. I mean 19 watts, 18.6. Here's its harmonic profile. We'll just take a peek at that right quick. That's with one spectrum program. That's the other one. Looks pretty much like the 300B, doesn't it? I have not listened to it yet. I just haven't. I don't think I can safely get it into my room. I'll have to have somebody help me move it in there. Its noise is 60 hertz noise is down 55 dB. That's plus 10, so it's down 65 dB. Should be okay. There's its second harmonic right there, 120 hertz. Okay, let's see. I'm trying to do the same thing on this one as we did on the other one. I guess the next thing to do is scan it. You've seen underneath it. Let me just start showing you the temperature of this thing, though. Look at the temperature of that tube right there. Man, that thing would burn you something terrible. I can actually see a slight bit of orange in it, and those are carbon plates, and you can see it here too. But it took putting in this 5881 6L6, whatever you want to call it, to get the voltage up high enough and the power high enough to drive the grid of these things. Okay, so I'm going to we're going to scan it and see how it turns out. Let me get it set up. Okay, well, I've already gone ahead and run it just to keep the video from getting longer and longer. It is pretty bizarre. Maybe not quite ready for production run yet. Looks like it drops below 3% here at about 20, 30, 40, at about 60 hertz. Gets down into the 1.5% from, oh, I don't know, maybe 200 hertz to 3 kilohertz. Goes back and look at this. Isn't that bizarre? It's going way up here somehow, and then at 20 kilohertz, 25 kilohertz, it's coming, both channels are coming back down. Look at that. That is the strangest thing. Now, I'll let it run again just so you'll see it. Let's do it again. Let's run this is the left channel. It's actually going to duplicate this yellow one. Watch this. This is just weird. And you know what? If I took it in there and hooked it up, I'd probably like it. It might sound okay. I don't know. Once it gets up to, let's see, what are we at? We're at 63 hertz, 70 hertz. I'll show you these. Yeah, see the red line coming down there now? See the red line right on top of the yellow one? We're just running it a second time. It's gonna retrace the left channel is going to retrace that yellow line, and the right channel is going to retrace that blue line. So we don't really have to go through all this. I'll show you what it looks like. Running. That's always kind of interesting to see. Let's see. We need to scoop out here, and then we can go over here to our harmonics and our fundamental and our harmonics. Actually, the harmonics don't look that bad, do they? They really don't. There's something really goofy about this thing. Let's look at it with this one. Well, I don't know which one's better. That one seems to take a while to settle down. I like the thinner line. But I noticed something on the HP spectrum analyzer that I want you to see. Okay, I think it's through. Yes, it is. Okay, let's do the right channel now. And we won't be staring at this thing right here, but that's it right there. That is pretty bizarre. So we just go down here to trace number 4. So it's right there. And when I click on that, there you go, starts running again. And then we can watch it. There's its power. Kind of goes up and down a little bit. That's a little weird. I can't explain that. There's its frequency as it's scanning upwards. It may not have time for the instruments to settle down either. So whatever it says is something close. It's about the best it can do. And here's what it looks like on a scope. Actually, it looks pretty good. See the frequency rising up. Let's see if I can turn the intensity down so it's not quite so bright on the scope. On the camera, speaking right there, maybe. Let me get my arm against that. There we go. We're up to 2500 hertz. See, it looks great, doesn't it? Okay, now look at this. I don't know how accurate this old HP is anymore, but it's because, guys, it's got a lot of fuzz or something down there in its noise floor. It's up to 20 kilohertz. Let's see, we gotta do it like this to see it. Well, anyway, we're not seeing much there, are we? Okay, well, it stopped. Okay, I got to plug this thing back in, being very careful because that thing would burn me big time. Well, anyway, ladies and gentlemen, that's I guess this one needs a little bit more work, but that's what it is at the moment. I've worked on this thing enough, and it's so heavy that I've pretty much lost interest in it. I guess I could take this choke load and this plate, this matching transformer out, and if I really want to take this thing any further, maybe just put these custom wound transformers in there, kind of start simplifying it a little bit. I don't know if I want to do that or not. I don't think I care anymore. I think I've lost interest in it. I think I've built about enough audio amplifiers for one lifetime. That's pretty much where I am. A lot of them I built, I wanted to test and see if the hoopla about all of these old transformers like the Acrosound, the UTC. I wanted to see if were as good as they were advertised. And what I found out, my personal experience, is I had at one time 10 of the Acrosound transformers, and out of the 10 I had to search very hard and measure every last one of them to find 2 that were close together. I don't know if that was, I've mentioned this more than one time in my videos, I don't know if that was aging or quality control from the beginning or just heavy duty use. I don't know, but it was hard to find 2 that were actually matched, and the 2 that I settled on certainly were not perfectly matched either. Now the UTC transformer seemed to be a little bit better at that. I did find that from my measurements, from building amplifiers and measuring on all this equipment here, I did find out that the Acrosound transformers seem to have a better low frequency response than the UTC, but the UTC has a better high frequency response. I think the UTC transformers are very nice. They're probably my favorite. I actually have a little amplifier in there that I built that I've shown before, but I converted it to 7591s. I'll have to show you. Let me take you in there and show you. Actually, I'll bring it out here and we'll measure it. Now that we've crawled around all over the tops of some SET amplifiers, let's look what a really nice little push-pull amplifier, how it performs. Okay, I'm going to show you the bottom side up first. We'll take a look at this because there's some things in here I want to point out. But this one's the same thing. So I put the schematic on the bottom. One channel. This is a Williamson amplifier. Runs 7591s. See, those are my hum balance pots. Of course, these are indirect heated filaments. You don't have to do the same thing to these filaments that you do of the directly heated filaments. Voltage doubler right here. Output transformer inputs. What's so magical to see about it? Really nothing. Well, one of the things that I did on this one is you can notice right there, see that little trim pot? That's the negative feedback. I trimmed that for very nice coners on a 1 and even a 10 kilohertz square wave. Same thing right here. So instead of just putting in a fixed one, I think the amount of capacitance was something like 80 picofarads. It's actually quite small. Another thing that I've learned is, see that little circuit right there, that little RC circuit. Those have been discussed a few times, and they are put in there to do one of 2 things. One is, in the old days, they were put in there and designed with a coner frequency to help eliminate AM radio stations from getting in to your amplifier. Well, I don't think we have to worry about that so much. And then they're also put in there at maybe like 70 kilohertz, because these Williamson amplifiers, these old designs with the components, the transformers, aging of components, whatever, tend to like to sometimes run at about 70 kilohertz. You couldn't see it and you couldn't hear it, but if you had a spectrum analyzer, it's there. Now the thing about it is you may not need it when you build the amplifier. And see, there's one over here too. It's right there. You may not need it, but as your components age, things can change. Oh yeah, one of the things I really got into these little pots. This right here is a cathode balance pot. It goes between the cathode of one output tube and the other, and the center piece goes off to the cathode bias resistor network right here. This is for one channel and that's for the other. And you set that for the minimum amount of distortion. This right here is, let me show you in the schematic. I think I actually threw it in there. It is, let's see, there's that little RC circuit. I chose to stop it at 21 kilohertz, 160 picofarads at 47K. I put in 12K grid stoppers, so I just kind of drew that one in. And I don't show it in here how I've got it set up. But oh yeah, I do right here. See, one of them's a 47K. A lot of times you see these this resistor with a little asterisk by it, and they tell you to match it within 1%. Well, the better way to do it is just set one, like 47K, and then this one is a 25K or 22K, and then a 25K pot. So you trim this one to where it matches this one by looking at the distortion on the output. So you can trim the distortion down very, very low. And then the same thing with this 25 and 25. You can't draw, I don't know how to draw potentiometers at LT Spice, that's why I drew it like that. But this is really a 50 ohm resistor with a slider. This right here is actually connected to the slider, which is those resistors right there. And then that's that one in series with the 22K to balance. See, there's the 22K. There's the 22K in series with it. And this circuit right here is to balance the 47K on the other one. Let's see, where's the other one? Grid plate cathode grid, this one right here. It's to balance with this resistor right here. And same thing on the other channel. This is the left channel and the right channel. This is a beautiful sounding little amplifier. Let me turn it over, put the bottom on, turn it over, and we'll test it. Okay, I'm just going to hold the camera for this. We'll just test one channel so we don't drag it out too much. What if I got it on the left channel up here? See, there's the left. That's right, well, doesn't really matter. I've got it adjusted for 5 watts at a kilohertz. That's what it actually comes up at. And then it says, are we ready? And I will say yes. Or say okay right there. And we'll watch this run. This is a Williamson design with the UTC LS57 output transformers. You see them on eBay. People are crazy over them. Sometimes pay stupid amounts of money for them. Now, I base I base my comments on low frequency response exactly what you see right here. This is not a bad thing. They sound marvelous. But at 20 hertz, THD's up at 2.2%. But you can see it drops rapidly down to 0.2%. I mean, this thing is performing very nicely. The Acrosound transformers do better over here. But as we keep going, and look at that, that's down at 0.2%. That's real hi-fi. No, that's some really good THD specs, that's for sure. And it does sound great. This is actually my favorite amplifier. Amplifiers are kind of like beer. You know, you get your favorite beer and then somebody gives you a different one. You go, I like that too. But sometimes you go back to your favorite. There it is, 20 kilohertz. All the way out to, there's 20, there's 25. At 20 kilohertz, it's 0.5%. At 25 kilohertz, it's 0.65%. So it is a marvelous performing amplifier. There you go. I don't see any sense in running the other channel. It'll do the same thing. And again, this is the 7591s. I got really charmed by them because my friend bought a MA225 Mac amp, and I just saw how well it performed. So that's why I went with this one. Those little RC circuits I put in there, I was telling you about to stabilize it. If you take them out, you'll actually get a little bit better high frequency response. Let's look at one more. Okay, one last one here. Maybe this is not a fair comparison, but I think it's kind of nice to see what actually vacuum tube amplifiers can do. I built this in 1977. It is a Macintosh MA230 channel. I bought the transformer directly from Macintosh for about 30 bucks. Wish I'd have bought more. Anyway, it's supposed to run 7591s, but I have built it up for EL34s. I've always liked the EL34. Let me show you what it does, and then we will scan it at 5 watts. Okay, here is its power. There's its sine wave at kilohertz. See, there's our kilohertz. There's our THD, 0.185 at 35 watts. If we, when we start overdriving a push-pull amplifier, see how it clips at the top and the bottom symmetrically? The SE amplifier just clips one side of it. So if we turn it back below clipping, our power is 43 watts and our THD is 1.5%. It's rated at 30 watts. If we turn it back to anything below its clipping level, even at 40 watts, it's only 0.4%. At 40, and that's its sine wave. Let's turn it back to 30, what they rated at. And vacuum tube amplifiers can perform quite nicely, can't they? 0.07, call it 0.08% at 30 watts. Okay, now let's run it to 5 watts. Let's see, now how do I do this? I've got to, I'm trying to do this without shutting the camera off. I'll take it out of here. I'll put it up here. Okay. Now I'm going to have to adjust the volume. Let's see. We got this set for 10. If I say start, then I've got to set the power level. And it'll say reference level okay. Yeah, actually it is. We sit over here. That's just a hair over 5 watts. I'll just hold the camera for all this, and there it is. And the reference level always starts at a kilohertz, and then it goes down, and we will scan it 20. We'll scan it the same way. Okay, now let's watch this guy. You see it starting out there. Look at its THD at 20 hertz. It's 0.1%. It's practically as good as the test equipment. It's pretty amazing, isn't it? Vacuum tube amplifiers can be as good as anything I think you ever put your ear to. And the truth being, I don't think the whole story is in THD and power. But you can see that it's unbelievably good. 0.1%. Pretty much all the way out, I reckon. Gotta bear with me now. So you can still see the little yellow line down here. 1200 hertz. We'll even run it at 30 watts just because we can. If nothing else, this also goes to show you do not have to always stick with one tube. Remember, this one was originally designed for 7591s, and I'm running EL34s. 12 kilohertz, 15 kilohertz, 20 kilohertz. It's up to 0.2%. 0.1%. There it is, 0.2% at 25 kilohertz. Let's run it at 30 watts just for the fun of it, what they rated at. Okay, I just stopped it for seconds just so I could get situated. Now we're still setting it to 5 watts. I'm going to turn up the gain right here. If I can get the screwdriver in it to 30 watts. Okay, there's 31 watts. I think that's going to be fine too, but there we go. There's our 30 watts. Our initial THD is a 0.1%. Let's run it at 30 watts and see how it runs. Okay, there it just starts out at 0.4%. Well, it came up a bit. Amazing what we did with amplifiers decades and decades ago. You know, amplifiers Well, let me put it another way. The vast majority of vacuum tubes were designed and built in the 1950s and 60s for television sets. The audio industry was a tiny subset of the electronics industry. It was TVs that ruled the world. So most tubes were made for TVs. I mean, even the mighty 6L6, I don't know if that was originally an audio tube or not. Maybe some of you guys know. It's done exceptionally well in the audio world. I know there was there's some nice articles out there about the KT, the kinkless tetrode. That's what KT supposedly stands for, kinkless tetrode. It was trying to get rid of that the crossover distortion, and I believe the British had a patent on it, and the Americans couldn't make it. So the Americans came up with the beam power tube. They used that third grid. Instead of making it a grid, they made it beam forming plates, which is what we live with today. And there it is at 30 watts. It crosses 20 kilohertz at 0.5%, right there, and at 25 kilohertz it's up to 0.8%. Well, anyway, that is my experience on SET amplifiers. I'm surrounded by amplifiers here. This one is just about the sweetest sounding amplifier I've ever heard. Do I think it sounds better than this? I don't know. Maybe I do. It's really hard to say. I'll tell you what, let's do. Let's look at something else. Let's look at the harmonic profile. We haven't done that yet. Let's get the harmonic profile. Let's run this thing up to about, oh, that's 50 watts. No, we can't do that. We're driving it just a little bit. Let's run this thing back down to 30 watts. Let's just look at the static harmonic profile of a high-end amp. This is the little Mac amp. Well, see, here's our fundamental. Look how far our whole herd of harmonics are. They're way down. This thing is up at about 5. About 5. Let's see, minus 10. No, minus 5. Minus 5. Second harmonics is down minus about 75. About 70 dB down. Third harmonic about 65. Fourth harmonic. Anyway, what's fundamentally different about this one and all the rest of them is just this whole harmonic group are way up here. They're up there at kind of like this in the SET amplifiers, and here they're just way the heck down. So THD is pretty much the determining factor. This one right here, I actually have a ouch. I actually have a cover for it. I have this guy right here, but I wanted to take it off to show you. I don't think it's necessary for me to go underneath it. Anyway, this goes over the top of it. I don't think I can put it on there with just my two hands. So please stay safe, ladies and gentlemen. Thanks for watching. I hope this is worth something. And stay safe, and see you another time. As usual, there is one more little thing I'd like to add here. I think the amplifier builder that wants to do the best they can with the hope for the most amount of success would really appreciate using LT Spice. It's free, and it's from a very reputable company, and it does a pretty good job. It won't tell you exactly how your amplifier is going to turn out, but it's a darn good place to start. I'm going to zoom in some things, and then I'll show you how it runs. I'm not going to try to give a course on it. Let's see, here's the input part of it. Okay, I got a kitty cat here in the way though. Let's see if I can get this big guy out of the way. You can change the value to anything you want, and you can simulate it. Here's our input circuit, our cathode resistor. I mean, I don't have to go through all this, but here's one of the things I want to show you about it. Is when you simulate it, I just think this part right here, if nothing else, This part right here is worth the whole darn thing. You go up here to where the little running man is, if you can see up here in the corner, and it runs. Okay, if for nothing else, let's just start out with the input signal, and we click once on it, and there it is. Now you can see it actually still running. Simulating. When you specify a voltage in LT Spice, it's a peak voltage. See right here, it already tells you that the total harmonic distortion is about 4%, right here at the very bottom. But we'll get to that in just a minute. Well, that's its input voltage, right here. I hope you can see where I'm moving the cursor. Now let's go to the plate of that tube and just click once. So see, now we have the input voltage and we have the output voltage. They're on the same scale, so of course the input voltage is quite small, but you see there you got that much gain. You can see that you know what the input is. It's plus and minus a half a volt, 500 millivolts, and the output of the gain of that stage, what you just built, is between about 24 volts and 33 volts. You know, that's, you can read it off exactly by putting your cursor on it and then looking down in the bottom right hand corner, bottom left hand corner. It's 33.89 volts. And then you can go to the next stage and click once on it. See my little marker here again. And there's the output of that stage. See, there's the input. The green is the first one. The blue is the output of the second stage. This is the output of the third stage. You can see it's much larger. It's between like 120 and 240 volts. Now let's go to the output of the 5881. There it is. So see, the input is so small on this scale, almost like a straight line. The output of the first stage. This is the input to the first stage, the output of the first stage. This will be the input of the second stage, the output of the second stage. And then we'll finally go over here to the output of the final amplifier. See, it's between just above 400 volts up to 1600 volts, probably the voltage of the power supply. So, you know, these lines down here they're not of much use anymore, but we can see 5 things at one time. Maybe able to see 6, I don't know. Let's look at the very output of it. Yeah, we can even see it. I'm not sure which one it is anymore. It's probably the other one right down here. But anyway, that's just one click at a time. If you double click, and there's the output. Looks pretty nice and clean, doesn't it? It's going between about minus 18 and plus 15. You can do just about anything you want with it. If you hold down control and you double click over here on the 8 ohm load, I'm double clicking right there to get its full output, and then I hold down control and click on this line up here that's voltage output of R13. It says I've got 18 watts. That's about right. 18 watts average power. You right click in the display up here, and you can go to view, and you can go to the error log, and you'll get that listing again. There's your harmonic distortion, THD 4%. You can also right click in it and go to view, and you can view the let's see, what was that, R13? Is it R13 or R18? Darn, I don't remember anymore now. Maybe R13? There it is. Yeah, see, that's its output. Now, is that going to be exactly what we measure in real time? Well, maybe not, but it's not bad. That actually looks pretty darn close. Because remember that slope that we had on the SET amps? And on the push-pull amp, all of these were much smaller. They were all down here. There's the second, third, there's that fourth harmonic. If I remember correctly, the fourth harmonic was actually quite low. So anyway, LT Spice is there's kind of a little bit of a tough learning curve there, but it's worth it. It's worth the trouble, in my opinion. So there you go. I just wanted to add that in. I'm not an expert on the LT Spice by any means, and I don't want to try to give a course on it. There are a lot of videos on it out there on YouTube. I don't know how good they are. You're just going to have to, if you really want to use it, you're just going to have to deal with it until it starts making sense. Thanks again.